Hi there, and welcome to another episode of Mr. Carlson's Lab. In this video, we're going to rebuild and improve an industrial CNC machine power supply. This power supply is known as a Yamabishi SFPW switch mode power supply, and this comes out of an FRSF drive unit. I'll also talk about the differences between the SFPW power supply and the SEPW power supply in this video as well. So let's get started. This is a Yamabishi SFPW switch mode power supply out of a drive unit from an industrial CNC machine. The power supply itself really isn't all that incredibly big, but it does a pretty big job, and we'll talk about that here in just a little bit. Just before I get into the repair and rebuild of this power supply, I need to warn you about a few things though. First of all, if you're following along, you're doing so at your own risk. Working on these power supplies requires you to be around high voltage AC and DC. This particular power supply requires a source of 200 volts AC or around. The reason I say around is because it will actually run off a broad range of voltages, but 200 volts AC is a nice center. That 200 volts AC is applied to these two white wires here. The green wire is just an earth. That 200 volts AC gets rectified and filtered by this large capacitor here, and we get high voltage DC all over this power supply inside. And this capacitor can hold a charge for a long time. So if you're unsure of working around high voltage AC and DC, this might not be for you. Again, if you're following along, you're doing so at your own risk. Just take care. The story on this power supply goes like this. The owner of the CNC machine that this power supply came out of bought this particular power supply 1 month ago online, and it was supposedly repaired by a reputable source, which had their sticker on the side here, and I've removed that because I'm not going to mention who they are. This power supply was to replace one that had already failed, so he actually has two failed power supplies right now. Of course, this thing only lasting a month, the owner got frustrated and tried to fix this thing himself, and he's included the part that he's pulled out of it saying that it's faulty, and I'll end up checking all that stuff as well. And that's understandable. When you buy a replacement power supply like this, they're expensive, and it only lasts a month. That's going to create some frustration. Now, the previous company that worked on this thing only replaced just a few capacitors here. There's two here that I can see, and there's a couple on the oscillator board under here, and we'll take a look at those here in just a moment. The original capacitors in these power supplies have PF written on the side of them. That's the series, and then there's a little M in brackets. So if you're looking to buy one of these power supplies online and they say it's rebuilt and it's working fine, or even that it's just working fine, if you see these capacitors in it, that's a big warning sign to you. All these capacitors are long since overdue. What happens is they develop ESR, and not only do they do that, but they actually physically leak their electrolyte onto the circuit board underneath. Now here's the catch with these power supplies. They'll run for quite a while with that electrolyte leaked onto the board. What that does is the traces are so close together, when there's a puddle of electrolyte there, it actually erodes the traces away and eats away at the circuit board while these things are actually running, creating many more failures down the road, in fact, even harming the drive itself. There's a lot of things that can go wrong in here. So all of the capacitors in this power supply, all the electrolytic capacitors, every single one of them have to go. They're all overdue, and they need to be replaced with a low ESR, high quality capacitor. So every capacitor that I'm going to install in this thing is basically hand graded. Every single one of them. I check every one before I put them in here. And that's just because I don't want the customer of this power supply to go down again. You got to understand, the customer that owns this power supply has a large machine that's supposed to be making him money. Right now, it's sitting there collecting dust because some other company hacked together a repair inside this power supply, and that's very frustrating for a company owner. So after this is done, it's going to be tested for 4 hours. I run these things for 4 hours to make sure that everything is good, repeatedly stopped and started, and all sorts of things. And that's very important because I want to make sure that this thing, basically after I rebuild it, lasts an extremely long time. In fact, I actually hope it outlasts the machine at this point. So all things to think about when you're working on power supplies like this. If you plan on repairing CNC power supplies, you cannot put cheap Chinese capacitors in here. It all has to be high quality stuff because the owner of this machine is depending on this thing to make him money. So what I'm going to do is remove the lid here. We'll take a closer look at what's inside this power supply and I'll explain the little sections here. So looking at the power supply sections in here, these two transformers here are for the drivers. All of these pins that you see here are for the drivers here. You can notice that they're little sets of 3. In these sets of 3, there's a positive 15 and negative 10 volt pin in each set. So that's what this section here does. This is completely isolated from this section over here. This is the main switcher transformer. In this row of pins, we have 5 volts, positive, negative 18, 24 volts, and an AC down signal. So if you were to ever try to work on one of these things, you want to be very careful that you do not short any pins to the AC down signal. This little circuit board right here is the protection circuit board inside this power supply, and this transformer here keeps it powered up all the time. So out of all the power supplies, I have to give this one here, a thumbs up, just due to the fact that this has got a lot of monitoring inside it. This is probably one of the most heavily monitored SFPW power supplies. I've come across a lot of other SFPW power supplies and, they're not protected as much as these ones are. So that's a bonus to this particular power supply. So again, this little transformer here is always on, and that's powering up this little protection board here. Again, if you short the AC down pin to any other pin in this little connector here, you're going to pop ICs on this board here, and you're going to have a whole different level of troubleshooting. Now, here's another catch. I've been working on CNC power supplies for quite a while, and I have to tell you that all the CNC power supplies out there do not have any schematics available. It's like it's some sort of a big secret. If you want to have a schematic for this thing, you're going to need to reverse engineer the power supply and draw something up. And that goes for all CNC power supplies. I haven't come across one CNC power supply with an available schematic. And if you find some little bits or pieces, usually there's lots of stuff hiding in little epoxy modules and things like that. So something to keep in mind if you want to start working on these particular power supplies. You'll probably need to end up drawing up one of your own schematics for something like this, and it is a little bit time consuming. So what else can I tell you about this thing? This little board here is the oscillator board, and this is what's oscillating the FET over here. There's a FET here, there's an SCR for a soft start, and there's a bridge rectifier on this, and these are just pinched against this heat sink here. So when the power supply goes back together, it's very important to put, a decent amount of thermal conductive grease, I guess we would call it, on here, thermal goo, whatever you want to call the stuff, on the back side of this, and then pinch it to the case so that there's, good thermal conductivity between this and the actual case, so it'll sink the heat. Same with this area over here. So these here are just rectifier diodes on this side over here. What else can I tell ya? Looks like these are the capacitors that other company had replaced on this board over here. So I'll have to take this board out and replace all these with high quality capacitors. These look like garbage. And before I put this particular board back in, this little oscillator board down here, I'm going to test this thing out. Now, if you're going to recap an entire power supply like this, it's very important to test this board out before you put it back in. Because if something is wrong on this board, there's an oscillating IC on here, a little oscillator. If there's something wrong with this, it'll take out the current sense resistor, it'll pop the FET, it'll do a whole bunch of damage inside this power supply. So you always want to make sure that this little board oscillates before you put it back in here. And we'll take a look at that here in just a little bit. So let's see, getting the circuit board out is relatively easy. You just remove all the screws on the bottom here. You can see all the screws. There's a screw here. Normally there's a rubber grommet here, and they're very easy to get in. You can put the rubber grommet on the cord, slide it down here, and then just pop it in like this. You see how they have this little cutout here? So you can just kind of pop it in, even if there is no rubber grommet or if you need to replace it. You'll also need to remove these screws here, and there's also some screws on the back that you'll have to remove right here. This one here, and this one right here. Once you've done all of that, the thing is pretty much going to come out except for that little plastic retainer back there. Do not break that plastic retainer. All you need to do is just pinch it together gently with a pair of pliers. This portion of the board here will just go pop out like this, and the whole thing will just come out, and you'll be pulling the wires through this little hole here. Of course, you're going to remove this little clip over here as well. And that's how you get the circuit board out. So what I'm going to do now is remove the little circuit board and take out all the capacitors, clean the board up, look for traces that have any issues. And when I have the capacitors out, or when I'm taking them out, I'll come back and I'll show you a little bit of that process as well. Okay, I've got the SFPW circuit board out of the case, and surprise, surprise. Looks like somebody's taken some sandpaper to the circuit board over here. Looks horrible in this section. I hope whoever worked on this thing didn't pull any plated through holes through. This is that little vertical oscillator circuit board right here. And you can see a fresh row of flux or resin over here. So somebody's also had this vertical circuit board out, which is that protection circuit board. Now, very, very rarely does anything ever go wrong on this board unless you do short some of these pins. So maybe somebody's been fooling around with this thing and caused some more damage. At this point, I really don't know, but this in this area looks really ugly. So I suspect that there's going to probably be some nasty issues happening over here. So that just gives us stuff to troubleshoot together. So this should be fun. So what I'll do is I'll set up some test gear and we'll start looking for bad parts. Okay, so let's start looking for some dead components. So I imagine that there's something really wrong in this area. That's probably why this has been worked on like this and scratched up like this. So one way to find out if the main FET is still working is just check that current sense resistor. And I don't know if you can see that in there. There's a little current sense resistor right down in there, and that's 0.1 of an ohm. So what I'll do is I'll just measure across that. That should be right about here. All right, is everything in focus here? Good. So here we go. $2.3K. So that's open. So there's a really good chance that that FET is gone as well. So that means that there's probably a lot of damage in this area just because that one resistor is open. So chances are it's a bad FET, bad current sense resistor. Chances are the IC on this board is probably gone as well. So very rarely do these things ever fail like this. They usually just shut off. You replace the caps, go in and replace a few other small components that are just standard to the rebuild, and the things work again, and they just keep working and working and working. So this one here is definitely due to tampering. That's the reason that this thing has failed. I see some scratching around the SCR here as well, so I'm wondering if maybe the SCR is, the soft start might be bad as well. So if the FET is shorted, it's pulled heavy current. There's a good chance that it's taken out that SCR as well. So let's see if I can get this FET desoldered here. Let's find out. So hopefully there's enough there for me to actually test this. I want to make sure that the pins aren't making any contact to the circuit board. Okay, so let's see if we can measure this in here, see what's going on with that FET. Maybe for fun, we'll just put it on a continuity. I have a feeling that this is a jumper, and yes, it is. Oh man, that's real bad. Yeah, so the gate lead is definitely shorted. This thing is, this FET is definitely a jumper now. So since it's shorted to the gate lead, there's a good chance that everything on that oscillator board, or a good portion of that oscillator board, is bad as well. So, yet to be determined over here at the SCR. Okay, well, I'll remove the FET and I'll take out the oscillator board, and maybe we can actually see some chunks missing out of some ICs and things like that. Alright, I've changed the tip in my desoldering tool so I can start desoldering most of the capacitors here. Before I did, The other tip I was using was large, and in order to get rid of this capacitor here, I needed that large tip, and that's the reason it was in there. So I just removed this first, and that tip worked very well for desoldering this FET as well, because the legs of this FET are pretty big. So now that I've got the smaller tip in my desoldering tool, I can remove this hybrid, but what I want to do first is add some fresh solder. I've put some RA-type flux on here, and I'm just going to touch this up. This looks really, really bad, so I just want to kind of freshen the area up just a little bit. So I'm hoping that, let's leave those. Doesn't matter if you bridge them while you're doing this because there's nothing here. I'm just going to desolder them. Now, I'm really, really hoping that they didn't pull any plated through holes through here. They look like they're pretty solid so far. I sure hope so. The reason that I'm putting this on there and letting it sit for a second is so that the solder melts all the way through the plated through hole onto the other side. And that's the reason that you see me putting it there, waiting a second, and then desoldering. Now, again, this all depends on how much solder that, he's applied to the other side. If he's, got a huge solder ball floating around on the other side, it'll take a little bit longer. And usually I can tell that this is loose right now because the whole thing is moving. So, you can see this here. This comes right out like that. So there it is. There's the little board right there. So I imagine that this is probably toast, this IC here. This IC is the one that's, this is the oscillator right here. I imagine it's probably bad. So what I'm going to do is just set some stuff up here and test this out, and I'll be right back. But just before I go, I just spotted this here. So he's pulled a pin off, or whoever has done this has pulled a pin off, and this is just ever so, I don't know, it's just hanging on there. So there's a pad on the other side that, that can be fastened to. And this is missing the one side, so what I'm going to do is just fix that up so that doesn't pull this little trace right off on this side of the board. I fixed the pins on the vertical board here, so I've just resoldered them. I haven't cleaned anything up yet because chances are there's a lot more things wrong with this. While I was at it, I measured across this one Zener diode here, and it measures 50 ohms. So I removed the Zener diode. It was mounted right there. I removed the Zener diode and just put it here on the bench, and I remeasured this again, and it still measures 50 ohms across this here, so I'm thinking that this IC is definitely bad. I'll also check this Zener right here as well. So what I'll do is I'll reposition the camera, and we'll take a look at that Zener and just test it since it's off the board anyways. The Zener diode is attached to the curve tracer now. It's in these little alligator clips right here. So what I'm going to do is advance the sweep voltage on the curve tracer. You'll notice a green line will move across the bottom of the screen. Each box on that screen represents 5 volts. When we get to 25 volts, it should take a sharp angle upwards if this Zener diode is working okay. You can also keep an eye on that digital display on the top there. That will indicate when we get to 25 volts. So here we go. Just advance the control now. And as you can see, the Zener diode is working. So I'll just bring this line down right to the point to where it takes the turn, and that's what the Zener voltage is here. So it's pretty touchy. So I'd say about 25.3 volts, which is absolutely fine. So that Zener diode is working great. So what I'm going to do is remove the other Zener diode off that circuit board now and test it as well. I have the second Zener diode attached to the curve tracer now, so we'll do much the same test. This one should be about 17 volts. So what I'll do is I'll advance the control here again, and when we get to 17 volts, it should take a sharp angle upwards. And there it is. So I'll back this down just to the point towards taking the corner. It's very touchy, right about there. 17.09 volts. It's working great. So both the Zener diodes are fine. Okay, let's test this IC and see if it's bad. We'll just do a couple of really simple tests here. So I'm going to test the output transistors that drive that FET from emitter to collector, which is pin 1 to 3 of this IC, and let's see what we get. "72 ohms. Right there we know that this thing is bad. So let's go from VCC to ground, which is 20 to 17. "52 ohms. Toast. So what I'm going to do is replace that IC. I have the IC removed from the circuit board now, and I've cleaned the circuit board up on this side and on the other side as well, and I'm pretty much ready to just put on a new IC and repopulate these 3 capacitors here. One thing I did notice when I removed the IC is on the circuit board itself there's quite a bit of scoring underneath that IC in this little area right here, which indicates to me that somebody's had that IC off to try and test it, or maybe they've even replaced it at one time. The IC itself does look original, so kind of interesting. Anyways, what I'm going to do is put on a brand new IC and populate those caps, and we'll try this thing out and see if it oscillates. Okay, I'm ready to install the new IC. So what I'm going to do is just flood the area with RA type flux. Grab the IC here. Actually, I'll grab my iron first. And I'll grab the IC. What I'm going to do right now is just tack it onto the circuit board here. So I'll just make sure everything's all nice and square. Make sure that I've got the IC on the board correctly. Because there's nothing worse than putting on an IC and realizing that you did a great job in putting it on, but it's backwards. So we don't want to do that. Okay, so there we go. So what I'm doing is I'm just going to tack one pin on each side. That's not quite centered. I think that's about centered there. And I'll just tack this pin over here. And I'm ready to solder. Give it a bit of a tap in the center of the IC just to make sure that all the legs are nice and flush on the circuit board. So what I'll do is I'll just solder a leg or two on this side. Then what I'm going to do is turn the IC around. Clean my tip. And I'm going to make sure that the IC is actually sitting flush, which it looks like it is. So just tack that one down there. And then I'll solder the leg right next to it. And I'll go back to this one here again. And now I'm pretty much ready just to solder the IC down. The reason I've done that is just to make sure that everything is sitting nice and flush. There we go. Nice and quick. And that's looking good. I'll just turn the IC back around the other way here again and finish off the other side. Nice thing about having RA flux on the circuit board like this is that it takes the solder so nice. And there it is. This one here could look a little bit better. There we go. The circuit board is all cleaned up now, and I've removed all the RA flux. So I'll just get a glare on the board so it focuses. So you can see it's all nice and clean now. And on the other side of the board, all the capacitors are installed. So let's try it out, see if it lives. The little vertical circuit board is ready to test. So I've got the scope probe hooked up to it and everything down there. So what I'll do is I'll just turn on the power supply, and there's life. It's working again. So I'll just zoom on into what it's doing here. You can see the frequencies, about 135 kilohertz. And peak to peak is about 17 point some odd volts, and that's limited by a Zener anyways. The duty cycle is about 45%. Rise time, we'll say about 43 nanoseconds, and the fall is about 35, 36 nanoseconds. That's actually faster than the original. Just a little bit, but not much. You know, brand new IC, right? So there's still a lot of things to test on this. There's still a lot of pins that need to be attached. So what I'll do is I'll just zoom on out here. Now what I'm going to do is just use the diode checker on my little meter here to test the rest of the functions. There's 3 functions that I still need to test on this to make sure that it's working properly. So I want to test the feedback. So what I'm going to do is just use the diode tester to turn on the opto here, and that should drop the duty cycle down. You'll see this thin up. So what I'll do is I'll just do this now. Get my leads in hand here. And so here we go. And there it is. Drops down to about 9%, something like that, 8%. So no problems. So that's working. So now I want to test the current limit. So I'm going to take my positive lead and attach it to the ground here and just touch the current limit pin. And what it should do is it should just drop the amplitude down. So here we go. There it goes. And I'll remove my probe lead and it comes back up again. No problems. Now the over voltage protection should latch the IC off. So what I'm going to do is just touch the over voltage pin on here and it should just disappear. There it is. So it'll just latch off in that protection mode. So what I need to do now is turn the power supply off. Wait just a moment and turn it back on again, and the signal should reappear. So everything is working as it should. So that's ready to be reinstalled back into the circuit board again. I'm ready to start the removal process of the electrolytic capacitors on the circuit board now. In fact, I've already removed some here. While I'm at it, I'll remove that FET because it's dead as well. Very easy to get it out. Just remove this screw right here, and this little bracket right here just comes off. So a lot of the times these gray boots are stuck to the heatsink. You got to be very careful when you pull on them because they tear very easily. If you tear the boot, you're going to have to replace it. So word of caution right there. So at this point, basically just choose a capacitor and start desoldering and work your way around. I get a lot of questions about my desoldering tool. It's a Heiko 470 pump with an 802 gun. Now, the Heiko 470 has an induction motor in it, and it's actually a really slow pump, but I designed a variable speed drive for it, and that's why it moves so fast. You'll also notice that it doesn't bog down at all when I'm using it. You can hear it's pretty constant. Lots of suction. I don't know if you can hear it squeaking. There's so much suction that it squeaks. You'll notice on the Heiko 472s and the pumps with the DC motor, you can hear quite a difference in the RPM of the DC motor as you're vacuuming. Kind of goes rare, 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 rare. So you can hear it bogging the pump down, whereas this has got a lot of power. It just does not bog down at all with that variable speed drive. The reason I chose the 470 pump over, say, the 472 with the DC motor in it is just because I don't want something that's going to wear. You know, the commutator on that is going to end up wearing out. It's going to go through brushes. This is an induction motor, so there are no brushes or anything really to wear. The only thing I'm going to end up replacing in this, which I already have, is, you know, the pump diaphragms and things like that. But it's a really handy tool. It works really good. So this is an 802 gun. The 802, I believe this one here, it's, putting on the years now. I think this gun is discontinued. It's the 809 that would be the replacement for this. So it has a little bit shorter stem on it, I believe. So it's the element that's hard to get for this particular one. So when this goes away, put it this way, this will probably last forever. My 936, Heiko 936, I've had this thing since the 90s. I have never replaced an element in this Heiko once. Of course, I've gone through tips, but never replaced the element once. And this thing here still appears to have the same element in it, so it's probably good for a very, very long time yet. Works very, very well. So anyways, that's a desoldering gun. I always get questions on that. So I'll remove all the capacitors and create a big pile of rubble here, and I'll be back. All the electrolytic capacitors have been removed from the circuit board now, and the circuit board is pretty much ready for cleaning at this point. So out of all the capacitors you see here that came out of this board, including that little vertical oscillator board, this is what they've replaced out of what they should have replaced. So that goes to show you, lots and lots of capacitors in here need to go. Now, surprisingly enough, only a couple of these PF series capacitors were leaking physically in this particular unit. Usually, most of them are. So that's kind of nice because it really didn't destroy the circuit board in this particular model. So, good high quality capacitors will go back in here after I clean the board, and then I'll be back. The power supply has all brand new electrolytic capacitors at this point. So all over in here, down in here, here, over in here. The ones on the switching board, the main filter capacitor up here, all have been replaced. The main switching FET has been replaced, SCR replaced, current sensor resistor has been replaced, a few other smaller ones on the board that have drifted in value. There's quite a few things wrong with this power supply. On the bottom, I've cleaned the board here already. So I haven't cleaned the posts yet here because I'm going to resolder those in the end, and I also haven't cleaned this little area right in here because that's where this little board has been taken out and put back in by somebody else, and I just have a feeling that this little board may have some problems on it, so I haven't cleaned this up yet. I might have to remove it anyways. I don't know if you can see that. So this might have to be desoldered. So what I'm going to do is I'll show you some of the dead components here. I'll just get the meter into the shot and I'll be right back. Let's take a look at some faulty components from the power supply. First up is the soft start SCR. Here it is. So in order to test this SCR, I'm just going to use my continuity tester. So I'll turn the meter to ohms, turn it to continuity, so it's audible. I'm going to zero out the lead resistance. So hold the leads together and just hit null. That zeroes that out. So now what I'm going to do with this component is test from the gate to the cathode. We'll see what we get. 0.03 of an ohm. This component has changed its function from an SCR to a jumper. Now, here's something interesting for those of you that may not play with SCRs a lot or haven't been working around them. We're going to test from the gate to the cathode on a brand new device. And this is what we get. 50 ohms. That's normal. No matter which way you put the leads, you're going to get 50 ohms from the gate to the cathode. On the continuity mode, if you test from the anode to the gate or the anode to the cathode, you're going to get nothing, no matter which way you put the leads. So that's how you quickly test in SCR. There are other failure modes for these things as well, but that's a normal SCR, and that's the way they look on a meter. So a lot of people get fooled by that. They see low ohms between the gate and the cathode, and they think to themselves, oh, it's turned itself into some form of a resistor. And well, no, there's a good chance it hasn't. When it gets down to 0.03 of an ohm or something like that, you definitely know the thing is toast. So the SCR in this power supply has been upgraded to a more robust device as well. So it's a little bit stronger and has a little bit better ratings than the factory unit. Things have come a long way since this power supply has been built. Same thing with the FET. The FET has also been upgraded. This is the switching FET that originally came in this power supply. And there's a newer device with much better ratings than this one in there now. So it makes the power supply run a little bit cooler and everything. So I'm going to do an episode on that as well in the future, how to choose a replacement switching FET for a power supply like this. There's a whole bunch of things that you have to look at in order to choose this. And of course, some of the most important things are, well, actually they're all important, but the input capacitance, or CISS, reverse transfer capacitance, CRSS, and if you even the output capacitance, COSS, is very important. Those are just a few of the things. There's a lot more other things as well. You need to make sure the voltage and current ratings and everything are all good for the device as well. Again, I'll do a future episode on this as well. So let's take a look at what this looks like on the ohm meter. Gate to drain, gate to source, drain to source. This one is an exceptional jumper. So this one here is really bad. And as you can see, from the drain to the source, that is just an absolute dead short. So that's why the current sense resistor gets blown. So it's a nice little fusible link. If that current sense resistor wasn't there, either the transformer winding would go away or the fuse. And believe it or not, a lot of the people that own these machines and these drives do not have the correct fuses in them. So that current sense resistor is very, very important. That is actually acting as the fusible link here. The reason that the main oscillator IC went is because there's a direct connection from that IC directly to the gate through a 5.1 ohm resistor. So if we look at the gate to the drain and the gate to the source, it's a dead short. So we know that we had a high voltage path directly right into that IC. I'm surprised there's, a chunk of that IC didn't blow out of it. So it was actually still intact. So pretty bad failure mode here. So now that that's all done, let's hook the power supply up and see if the thing will start and get an idea of, if we're going to have to search a little further, or, maybe it's even working at this point. Let's test out the power supply and see if it starts. So I'll just explain what I've got going on the bench here first. So this device here mimics the drive that the power supply came out of. This device here is a test fixture that allows me to link this power supply to this device over here. These two wires here are connected to my variac and isolation transformer supply so that I can give this power supply 200 volts, which is what it needs in order to operate. So keep in mind that whenever you're testing a power supply like this, you should always have an isolation transformer just to keep yourself a little bit more safe. There's a lot of things involved in the safety aspect of working on stuff like this that involves high voltage. So again, if you're following along, you're doing so at your own risk. So what I'm going to do now is turn on my isolation transformer variac supply, and it's in a current limit mode right now. And now that it's in that current limit mode, if there's anything wrong with this, say it starts up funny, or say it's not oscillating, or maybe there's even a short in a switching transformer or something like that, what it's going to do is it's just going to trigger the current limit. So here we go. Turn on the supply. Now I'm going to slowly advance this to 200 volts AC. And I'm already about halfway there. And now, right now I'm at 200 volts AC and nothing is happening. So that tells me that there's still some issues on this board. Could be this little board here that other person had removed, or maybe there's some other components down on the main board that are still haywire. But that gives us some more stuff to troubleshoot. So what I'm going to do is reposition the camera and we'll look for those problems. The first step in diagnosing this power supply is to see if the startup circuitry is working. And the startup circuit is right down here in this little power supply right beside the oscillator board. This is how the startup circuitry works in this power supply and many other switch mode power supplies as well. So when I first turn on the 200 volt AC mains, this little circuit down in here supplies about an 80 to 100 millisecond supply voltage pulse to this little oscillator board. That's enough time to start up this switching transformer. And at that point, this switching transformer takes over and supplies the correct voltage, which is 18.5 volts, to the supply for this little oscillator board here and keeps everything running. So in a way, this is kind of like a little kickstart circuit. And if that little circuit isn't operating correctly, nothing is going to happen. So in order to easily test this with basically no test equipment or anything at first, is to turn on the AC mains. If I see this pulse or any of the little test fixture LEDs pulse, just for a brief second, I know that that startup circuitry is most likely working. if I click on the AC mains and I see no pulse of this little yellow indicator LED or the test fixture LEDs, then I know chances are that startup circuit isn't working. So I'll click on the 200 volt AC mains and we'll see if we see an LED flicker right now. And there's absolutely no LED flicker there whatsoever. So that tells me that there's a very good chance that the startup circuitry in here is not working, and that's what we're going to troubleshoot first. The first thing I'm going to do is test this transistor right here. And I'm going to do that right in circuit. Now there's no AC mains applied whatsoever, and this capacitor is completely discharged. Very important because the collector of this transistor has full DC across it, and that's up in the high 200s if this capacitor is charged up, and that'll very quickly destroy my meter, and I don't want to do that. So everything's discharged, and I'm just going to test this in circuit using my diode checker. Very simply, take the positive lead of your diode checker, put it on the base of the transistor, since this is an NPN. Take the negative lead, touch it to the collector, and I should get a beep. No problems there. Now I'll touch the emitter, and I should get the same beep. No problems at all. So that transistor is okay. So next, what we want to do is start testing for voltages and see what the voltage on the oscillator board actually is at startup. In order to better understand how the startup circuit is operating in its failure mode, we're going to use an oscilloscope. So basically, we're going to compare two events. We're going to compare what we know is supposed to happen to what is actually happening now. I can't stress how important this is in effective troubleshooting. You not only want to know how the circuit is supposed to work, but you also want to know how it's working in its actual failure mode, if it's even working at all. By doing this, it allows you to troubleshoot quicker down the road in the future if you ever come across, say, the same power supply, or say you're running across the same kind of circuit in some other power supply or whatever you're working on. You can go, oh, hey, I remember that it was doing this exact same thing, and it'll almost immediately lead you to the problem. So very, very important to understand the actual failure itself. It also leads you to improve the circuits and things like that. And again, in the future, I'll get into dedicated videos just about this particular subject. So right now, I have my oscilloscope hooked up to the negative of the circuit here. So this is a common lead of my oscilloscope probe. The signal lead of my oscilloscope probe is hooked up to the emitter of that transistor that we've just tested. So we'll take a look at the oscilloscope screen here. So we know that we're supposed to have about an 80 to 100 millisecond pulse, and the voltage should be up around 18 volts. Now here's the key, around. All of these power supplies will vary just a little bit, and it's really common, especially in these little startup circuits here, for to be around that. So we'll say between 17.5 and 19 volts somewhere. Nothing's really written in stone, right? So what I'm going to do is turn on the AC supply to the power supply right now, and we're going to see how this startup circuit works. The scope itself is set just to capture what happens at startup. And if I haven't mentioned this already, the scope is DC coupled into the circuit. So here we go. I'm going to turn on the AC mains right now. And I'll shut it off. And as you can see, this is much, much different than what we're supposed to be seeing. You can see our max voltage here is up around 10.4 volts, nowhere near enough to make that little oscillator board start up. It's supposed to be up around 18 volts. The board itself will start about 15 or 16 volts, but it won't be reliable in that area. It really needs to be about 18 volts to be reliable. And as you can see, at 50 milliseconds per division, at this point here we're already at 100 milliseconds, and it's just staying on at 10.4 volts. It should have come down by now. So again, being about 100 milliseconds worth of pulse here. So what we need to do now is look at what's controlling this transistor. So trace our way back to what's controlling the transistor. So we're going to follow from the base lead of the transistor back. There's also one other component in this circuit that can affect what's going on here, and I've noticed that it has been replaced as well before I've had my hands on the power supply here. So that leaves that component suspect as well. So what I'm going to do is just remove the scope, flip the circuit board back right side up again, and we'll start tracing back from the base lead of that transistor that we've just tested here and see if we can find an issue. The first suspect component here is the transistor that I noticed has already been replaced, which is now an NTE25. The original part number for this is A1020. So one little trick here is whenever you're looking at transistors and you see an A and a B, or a C and a D and then a number, that tells us a lot about the transistor already. So A's and B's are PNP transistors, and C's and D's are NPN transistors. Since this was an A1020, we know that this already is supposed to be a PNP transistor. So that part number is also not complete as well. So whenever you see a transistor with A, B, C, or D, put 2S in front of it when you're looking it up. So 2SA 1020, or say 2SC 945. So usually what's written on the transistor would only be C945 or A1020. Now this NTE25 transistor is the correct replacement for that A1020. So what I'm going to do is just remove this and test it out first. So that's what I'm going to do right now. So that transistor is right here. So I'm just going to desolder it. Okay. So now, in order to test this, I'm just going to put my diode checker on here. There we go. So the base lead on this transistor, get this all in the shot here. The base lead on this transistor is the far lead over here. So this is a PNP. So we know that we need to stick the negative lead of my diode checker on the base lead of this transistor. So here we go. 0.6 of a volt, no problems, and 0.6 of a volt, no problems. So the transistor is fine. So the NTE25 still lives. So what I'm going to do is put this back in the circuit and we'll start troubleshooting elsewhere. What we want to do now is follow the base lead of this transistor that we've just tested to be okay back to any kind of device that's in the way. So by putting our continuity checker on the base lead, I found that it runs right over to the cathode of this C1093. Now, here's another trick. This is not a transistor. This is a programmable voltage reference. So whenever you see an IC, an integrated circuit with a C starting as a number and then a number, put UP in front of it. It's actually a micro symbol, but UPC 1093 is the part number of this little programmable voltage reference. So that's the next thing that's suspect on the list. So you can hear it beeping there. So this is what we're going to look at next. So I'll just remove this. Okay, I'll remove this component so that we can test it. So where did it go? I think this is the one here. It is. So this should test as basically two diodes, and it should read way up in the mega ohms if we test this thing in. It's going to be working correctly. So I'll get the meter in here. We can get both of these things in the shot here. Okay, that looks about good. All right, so I'm on ohms right now. So when I test between the leads, it should test up in the mega ohms. So I'm going to put the negative lead of my ohm meter on the cathode of the device. All right, and it should be in the megs. And it's 9K ohms. Let's go to the reference pin. 1 meg. So 9K ohms is not looking right. So now this should test as two diodes, really. So again, the negative lead of my diode tester is on the cathode of this reference. Here we go. And it's not even testing as anything. And then to the reference pin. Ooh, it's not testing as anything either. So I imagine that this component is faulty. This is a good device right here. So to give you an idea, cathode, negative lead here. All right, should test as a diode here. So that's to the anode lead. And then to the reference pin, it should also test as a diode. And then if we go to ohms here, we should see that it's in the megs. Almost non-existent. If we reverse the leads here, I'll get a meg ohm reading. There we go, 1 meg. And then about the same 1.4 megs to this one here. But the diode test is very effective for testing these things. So this is faulty. So I'll just replace that and we'll try out the power supply again. With that new component installed, let's see if the supply starts up. So here we go. No problems, it runs. But I have noticed one other issue, and it's still not working correctly. So what I'm going to do is just reposition the camera here and explain exactly what I've seen. In order for this power supply to operate correctly in the drive, it's absolutely crucial that the AC down signal is performing correctly. The AC down signal is indicated by this LED right here. So when I first apply AC voltage to the power supply, all these status lamps should come on. This should just briefly flash and completely extinguish. When I shut the power supply off, it should flash again to full brightness and completely extinguish again. So keep an eye on this LED and I'll apply the AC voltage here. So here we go. And as you notice, it's kind of just coming on and staying on. So when I shut the power supply off, it should flash and go completely off. And you can see that it's basically not doing that. The way that this circuit operates also affects the way that the driver voltages get applied. So it's crucial that this one circuit that operates the AC down signal is working properly. And in this power supply, it definitely is not. Now, the reason that this happens almost always is because somebody has shorted some of the leads here. So on the actual power supply, they've got their voltmeter or something in there and they've touched the leads together or something. And what that does is that pops the ICs on this little vertical board here. Now, if you remember correctly, I didn't clean the flux off the bottom of the board here just because I suspected there might be an issue on this because it has been removed by somebody else. And sure enough, the ICs here are destroyed. So I need to remove this vertical board and replace those ICs. And that's what I'm going to do right now. Hopefully that rectifies all the problems in this power supply. The small vertical board has been removed from the power supply now. And I can tell just by looking at the ICs here that somebody has been probing around and it looks like some of the leads have been resoldered. So that's a good excuse just to replace everything on here. One other thing to keep in mind is whenever you remove a board like this from another board, this stands vertically, right? All of these connections here need to be resoldered on this board here as well, because when you heat the pin to desolder them, a lot of the time it puts small cracks in the solder on this board here, and it could end up being an intermittent connection. You definitely don't want that when this thing goes back into service. So all of these little pins have to be resoldered on both sides of this board as well before it goes back in. The small vertical board is reinstalled in the power supply, and I'm now ready to test it out. So keep an eye on the AC down LED and the LED that indicates the positive voltage for the drivers. Keep an eye on both of those LEDs right there and notice their action. So I'm going to turn the power supply on right now. Now you'll notice that this LED fully extinguished before the positive voltage was allowed to come on. That's crucial for the health of your drive. You'll notice that it's also fully extinguished and it came to full brightness. That's how it's supposed to work. Now, when I shut the power supply off, so basically I'm just turning off the AC mains, I should have a flash on the AC down LED again, and you'll notice that the positive side will go out before the negative side. The negative side will linger. That's also crucial to good drive health. So here we go. And now that's working correctly. So Everything in the power supply is working good now. Just to finalize things, I'll do this off camera because it's kind of boring. What I'll do is I'll end up adjusting the 5 volts, make sure that it's right at 5 volts. I also will readjust the current limit for the 5 volt supply because I've changed out that current sense resistor. So I'll check that to make sure that's okay, and I'll also adjust the AC down to make sure that it's actually within spec to where it's supposed to be. That's pretty much it. All the driver voltages I've already checked. Everything is good. And that's, again, kind of boring off camera stuff. You can get the specs for that right out of the manual for this. It tells you what the driver voltages are. One word of caution, if you're going to be testing any of these things, you need to be leery that, there's obviously going to be 200 volts AC applied or around there to this power supply when you're doing that. So be very careful with your probe leads. And again, don't short anything out. It's important to have very short probe leads. So if you have tips for your voltmeter, something like this with just a little bit of tip exposed here, that's really safe. So if you slip, you can't really short anything out. A lot of people, when they're testing these supplies out, they have these long exposed ends here on their probe lead, and it's very easy to come across 2 terminals, and of course that will damage the power supply. And as you can see, all it takes is one slip of a probe and this entire circuit board has to come out and the ICs need to be changed. So that isn't an easy task. Let's take a look at the start circuit in this power supply when it's operating correctly. So the upper trace indicates that start circuit pulse. The lower trace indicates the switch mode transformer taking over. So I'll turn on the power supply. And that's what we get. Just ignore these little spikes over here. It's because I have the probe leads laying right over the switching FET. So we can see here, this is the start pulse, and this is the switch mode transformer starting up here. So you can see just a little bit past the center line here, the switch mode transformer is starting. So the pulse starts here, it gets to about a peak. Right about here, that switch mode transformer starts up. And as you can see, it kind of tapers off a little bit and then it drops off abruptly. So at the point to where it's dropping off abruptly is where this switch mode transformer is taking over and keeping that little oscillator board running. So if I turn on the cursors here and I go with, say, vertical bars, I'll move this over to here, about there, and I'll move this over to about the start. It's right about at the beginning of the climb. So 81.5 milliseconds is the length of this pulse here. So that's absolutely perfect. Now, again, it'll be a little bit different for different power supplies. Some might be 85 or 90 or maybe even 100. It really just depends on, component variation and things like that. So that's how a normal start circuit works in this particular power supply and many other switch mode power supplies as well. The power supply is all put back together, and now it gets to run for 4 hours. So, in the meanwhile, I'll get started on the next one. I've started removing the capacitors on this second power supply, and you can see how incredibly bad these capacitors are. They're all leaking around the bottom. And what that's doing is that's depositing that on the circuit board. There's actual wet spots on the circuit board. I don't know if you can see that, and there's a little bit over here as well. So that means that you need to clean the circuit board very, very well before you reinstall the new ones. It actually erodes the traces off the board. Some of them are extremely bad. I just desoldered this one and the leg fell right off. It's actually rotted its own leg right off. This is very common for this early series of capacitor, this PF series capacitor. So if you have any test gear or any power supplies that have this series of capacitor in them, I strongly suggest by now that you start replacing them, or you're going to start dealing with this and it'll destroy the circuit board underneath. So when you're choosing a new capacitor, you want to look at things like ESR, ESL, and ripple current ratings. And put something new in there, good high quality capacitor, so you don't have to worry about that for a very, very long time. Now, this particular series of capacitor, I see them leaking all the time. It's, I'm really surprised if I don't see them leaking, put it that way. That's how incredibly bad these things are. So there you go. Hope that helps you out in your preventative maintenance. Thanks for stopping by the lab today. I hope you enjoyed the repair and rebuild of this SFPW power supply. If you're interested in repairing industrial CNC machine power supplies or just learning a little bit more about electronics in general, you might want to check out my Patreon page. Just below this video is a Show More tab. Click on that Show More tab and I'll have some links under that for you there. If you enjoyed this video, you can let me know by giving me a big thumbs up and hang around. I'll have many more power supply videos coming in the near future. So until next time, take care. Bye for now.